what we will take as a beginning. So we will first write down a formula for the horizon and then see what are the problems that we encountered with this concept. So again we look at radial motion of light, okay, because the homogeneous and isotropy allows us to imagine that the source of light is at the origin and you want to see how far it is travelling in the radial direction. So we have the equation dt over at as dr over square root of 1 minus dr square. So integrate from the beginning to any time t 0 to r of t. So this quantity is what I call RH of t. This is the distance in co-moving coordinates that light has travelled. So we get a formula, or let me call it RH, capital R. Capital RH of t as integral 0 to t dt prime over at prime. Which I can also write as 1 over a naught times integral 0 to t dt prime over at prime. This is of course not the physical horizon size.
So
yes.
So this is the dimensionless. So RH is the integral.
RH is
So this integral is they are dimensionless because r above and both are in the numerator and denominator.
yes.
But that RH is just a number, not the.
Yes. So that's what I'm saying. So this is the horizon in the co-moving coordinates. Okay. But we'll now see what it is in the physical horizon. Okay. So the physical horizon at a given time t, at time t, this is given by A of t times RH of t. Right? Because at any given time t, the metric has a factor of A of t multiplying the dr square over 1 minus dr square factor, A of t whole square. So the physical horizon is given by this product. Right? This is the physical distance. So this is A naught times lambda t. So we get this as lambda t times integral 0 to t dt prime over lambda t prime. Okay, so these are the correct dimension of distance. Is this clear? Yeah, this is just the horizon, okay, measured in co-moving coordinates, how far light would have travelled in the co-moving coordinates. This is the real physical distance that light travels at any given time. So RH and the actual horizon of course is very simply related.
So
this is called dH of t. Yes.
So what is the small r? This.
Smaller is the radial, that's the same coordinate that we introduced. The metric ds square is minus dt square plus A of t square times dr square over 1 minus dr square plus r square d theta square plus sin square theta square. So that's the small r. Okay, I am assuming that it goes radially out from 0 to capital R, 0 to small r. Right? That's how I integrate here. See, if light propagates along the null geodesic, right? Then you know that along the propagation you have dt is equal to A of t times dr over square root of 1 minus dr square. Right? This is the equation that I have used, and I have integrated this from 0 to t on this side and from 0 to r on that side. Okay,
So I
Which
was
means-
thinking that smaller should be capital RH. Because-
Well, that will be capital RH if this k is 0. Then this integral is directly r t. But because of this k, this is not directly RH, right? But it's simply related to RH. Okay, the small r and capital R are slightly different because of this k. If you say k equal to 0, then they are the same. Is this okay? Okay. So again, let me repeat that the physical horizon is this one. Okay. Nevertheless, RH is a very useful concept for reasons that I'll explain. Okay. So you'll be working mostly with RH. Okay. But at any time, if you want to know how much the physical horizon size is, you just have to multiply by A of t. Okay. So why is RH useful? RH is useful, okay, because you can see the utility from this formula as integral 0 to t dt prime over A of t prime. RH is useful because it acts. Okay. Namely, imagine that you have some era in which one particular equation of state, or say radiation dominated. Okay. You calculate RH at the end of the radiation dominated era by integrating from 0 to the end of the radiation dominated. Okay. And then now suppose you have matter, you go to matter dominated era. Then you calculate the corresponding integral from beginning of matter domination to whichever time you want to calculate. Okay. So RH, if you want to calculate at the end of matter dominated era, right, you have to calculate the contribution from the radiation dominated era and add to it the contribution from the matter dominated era. Okay. Whereas if you had multiplied by this d lambda of t in the middle, right, then at the end of the matter dominated radiation dominated era, okay, dH will be lambda at the end of radiation dominated era multiplied by this RH. Right. So that will not add to what you get from the matter dominated era, right? You have to first divide by lambda of t, okay, then calculate RH from the matter dominated, add it, and then multiply by the lambda of whichever era you want to calculate it for. Okay? So that is the reason why RH is a useful thing to work with, and I'll be working with RH. Okay? But at any time, if you want to know what the physical horizon is, you just have to multiply back by A of t.
At that time.
At that time. Okay. But we will be comparing distances. Okay, so RH is good enough for us. Okay, if you want to compare two distances at any given time, okay, then this A of t doesn't matter. Just multiplication by A of t. Okay. So now what we are going to do is to calculate how much RH changes in a given era. Okay. So let's imagine that, consider some period in which rho goes as C, rho equal to C over lambda to the alpha.
Sir, just one question.
Yes,
And we are calculating the distance light would have traveled from the beginning.
yes.
Then shouldn't the upper limit be my horizon distance? Means the upper limit of the
That was-
integration.
That's what I was also.
Yes. So the point is, so I'm calling this integral RH.
So we are some function of r.
Yeah. So the point is, if k was 0, then this upper limit will be exactly RH.
Yes, yes,
Right? But because k is not 0, right, if you want to measure the physical distance in the co-moving coordinate,
yes, yes.
is this integral is what I'll call RH of t. Okay. See, the upper limit is the actual value of small r to which it travels.
Yes, yes.
Yeah.
But the value of small r doesn't fix the distance, the three-dimensional distance in this r theta phi coordinate system.
So this is because the
So
matrix.
even if you take this out, right, the distance in this metric from 0 to r
Oh.
is integral of 0 to r this object, right? dr over square root of 1 minus kr square.
Okay.
So this is because of the metric.
Because of a metric. Okay. But as I said, for all practical purpose, you can just set this k equal to 0. So there is really no difference in that sense between smaller and capital R. Okay, you could have called it smaller h and set k equal to 0. Okay. So let's consider some period in which rho goes as c over lambda to the alpha. We already know, for example, that lambda equal to 4, alpha equal to 4 for radiation dominated, and 3 for matter dominated. For cosmological constant, it will be 0. Okay, now whatever you are going to do is not strictly valid for 0, so you have to think of this as some kind of limiting case. So if we take rho equal to c over lambda to the alpha, we can now integrate. Okay, we can see how lambda behaves as a function of time. So let me write the equation for lambda. So lambda dot over lambda square is 8 pi g over 3 rho. So rho is c over lambda to the alpha. Lambda to the alpha, as we are taking. So by taking square root, we get lambda to the alpha by 2 minus 1 lambda dot square root 8 by g over 3, 8 by g c over 3. This can be integrated to give 2 over alpha, lambda to the alpha by 2 is square root of 8 by g c over 3 times t plus k. Or lambda, lambda from here is alpha over 2 square root of 8 pi g c over 3 t plus k to the power. This whole thing dot 2 over alpha. Is this okay? Okay, so this is what we get if rho goes as c over lambda to the alpha in some era. But this calculation, of course, we had already done earlier, right? Our interest is in calculating RH. Okay, so we will now substitute in the expression for RH this integral and calculate it, which is again not very hard. So RH of t is 1 over a naught integral dt prime over lambda t prime, okay, 0 to t. But of course this formula may not be valid all the way from between 0 and t.
Into some intermediate region, it is not valid.
Yeah, intermediate region of course is not valid, but what I am saying is that if you do from 0 to t, right, then for some part of the range there will be one formula, for another part there will be another formula, and so on. Okay. So if you want to make use of this formula, what you can do is to calculate RH of TF minus RH of Ti, where both Tf and Ti are within the domain where this formula is valid. Then you can calculate, right? Because then the integral that you have to calculate is lying fully within that domain.
So this Ti is the time from which the domination of
We will take it, eventually we will take that way. Right now Ti and Tf can be two arbitrary points in time inside this domain, okay, where this form of rho is valid. Okay, later on we will try to sketch it and take it all the way to the beginning and end. In this case, so Ti and Tf are two arbitrary time intervals right now, okay, within this domain. So this will be given by 1 over A naught integral Ti into Tf dt prime, and now for lambda t prime I can substitute this. So alpha over 2 square root of 8 pi gc over 3 this inverse and t plus a, or t prime plus a to the power minus 2 over alpha.
So to what 8 pi gc, there is also 2 over alpha minus.
There is also
minus 2 over alpha.
Minus 2 over alpha.
oh minus 2 over alpha. Thank you. Minus 2 over alpha. Yes. Is this okay? I just substituted this form of lambda. Then this quantity alpha over 2 square root of 8 pi gc over 3 raised to minus 2 over alpha, and then you get a factor of alpha over 2 minus alpha, I think, and t prime plus k to the power 1 minus 2 over alpha between Ti and Tf. Is this okay? This came from the integral, right? This is basically the same factor, 1 over that factor, alpha over alpha minus 2.
Alpha.
So this we are going to analyze. So this is Tf plus k to the power 1 minus 2 over alpha minus Ti plus k to the power 1 minus 2 over alpha. And now the idea is that we will try to re-express it back in terms of lambda. Is this clear? So this quantity is given, or maybe let's say one of them. This one is given by lambda f. The lambda f is the same as lambda tf. First, let's do the tf plus k. Okay. Alpha by 2, then alpha by 2 square of 8 pi g over 3 inverse minus the same thing with lambda I. Is this okay? Okay, it is just straightforward algebra. We just are replacing Tf plus k in terms of lambda f, okay, which is lambda of Tf, and Ti plus k in terms of lambda I, which is lambda of Ti. So let's simplify this a little bit. So 1 over a naught. Now you see that this quantity 8 pi Vc over 3. So let's calculate the total power of this, right? Because this can be taken out of both have the same common factor. So this is minus 2 over alpha, and here we have minus 1 plus 2 over alpha. Minus 1 plus 2 over alpha. Is this okay?
Minus 1.
And then alpha over alpha minus 2, alpha over alpha minus 2, and then you have lambda f. What is the power of lambda f? Alpha by 2 times this. So that's basically alpha by 2 minus 1 minus lambda I to the power alpha by 2 minus 1. So you can simplify this a little more. 1 over a naught times okay, this looks like a simple enough formula. In fact, you can probably simplify it a little more. Okay, so let me do that. This is 1 over a naught. You see, this alpha over 2 becomes 2 over alpha, so that becomes 2 over alpha minus 2, 2 over alpha minus 2, 8 pi g c over 3 to the power, I can write it minus half, and then lambda f to the power alpha by 2 minus 1 minus lambda I to the power alpha. Okay, so this is the final formula that we are going to use. Now, we will see that both for matter and radiation, okay, for alpha equal to 4 or alpha equal to 3, this quantity alpha by 2 minus 1 is positive. Okay? Which means that since lambda f we expect to be larger than lambda I, right? In fact, if you wait sufficiently long, lambda f will be much larger than lambda I. Okay, that's typically the domain, because in a given domain, typically lambda expands by a very large amount. Okay? So you expect that this term will always dominate over this term, right? Because it's positive part here. Okay? And for most practical purposes, if you are interested only in the order of magnitude analysis, you can drop the second term. Okay? And this is the result for the horizon.
So when we say sufficiently long time,
Yes.
we cannot take TF and TI to be very much apart because
No, that's true. But the point, even if lambda jumps by a factor of 10, right? This will be like 10 is to 1, right? For radiation, for example, it's 4 by 2, which is 2. Right? It's 10 is to 1, right? 4 by 2 minus 1 is 1. So if lambda jumps by expands by a factor of 10, right, this is dominant by a factor of 10 over this. If lambda expands by a factor of 10 and if it matter dominated era, right, then this is square root of 10 versus 10 versus 1. Right? Square root of 10 is still 3 times larger than this one, right? So for order of magnitude estimate, you can still drop the second term. Okay? And right now we'll be mostly interested in order of magnitude estimates.
So that's why it doesn't matter where you take the initial position.
Yeah, that's why it wouldn't matter where you take the initial position. Okay, but we have to do a little more work to make this even more concrete. Okay. So this says that for matter, if you are within a certain domain, say matter or radiation, right, then it doesn't matter that much where you began, right? Whether you began exactly at the end of radiation dominated era or maybe a little later than the end of radiation dominated era, it doesn't matter because that difference will contribute very little, okay, compared to the total contribution. But now let's do a little more work to see what happens as you make transition from one region to another region. So let us suppose that this is our time, and as the universe expands, at some time t, it goes into one era which are labeled by B, into another era which is called labeled by A. Okay. For example, from radiation to matter, right? We know that would have happened at some point, so, but right now we are just not specifying what era it is. Some era to some other era, okay, B to A. Now, in this region, of course, both B and A will dominate, right? So it's not that there is sharp transition from B to A. Okay. Nevertheless, because again we are interested in the order of magnitude estimate, okay, we can pretend as if there is a sharp transition from B to A. Okay, that at some point B ends and A takes over. Okay, we will be making some error over here. Okay, but that's again an order 1 error. Okay, we will ignore it for now. Then how do you proceed? Okay, then how do you know how it evolves through this? So you have to find some formula that connects the variables on this side to the variables on that side. So what are the formula? First of all, lambda of course is the same here, right? Okay. So if this is the final point of B, we will say the lambda f of B is the same as lambda I of A. Final point of B is the initial point of A, and hence the lambdas must be equated. But there is also something else, which is that rho f of B should be rho f of A. So after all, A takes over B because their energy densities are equal. Rho I of A. Okay. This transition takes place when the energy density in B and A components are equal, right? So we have to equate rho on the two sides. Is this clear?
So rho I will be like a matter one and rho f will be of a radiation.
Exactly, right? So if this is the matter radiation equality time, that's when you go from radiation dominated to matter dominated era. Okay. By definition, matter radiation equality means that the total energy density in the matter is the same as total energy density in radiation. Right? On this side, radiation is more dominant, on this side, matter is more dominant, but here they are equal. Okay, so we equate these two. Is this clear? So let's see what this implies. So this is CB over lambda f to the B to the x. So this exponent we will call beta. Okay, and this is CA over lambda I to the power alpha.
Hmm.
Is this clear what you are doing? Okay. CB is the corresponding coefficient C, the same coefficient C. See, the C appeared because we took rho as C over lambda to the alpha, right? Now you are saying, let's suppose in B, rho is CB over lambda to the beta, and in A, rho is CA over alpha to lambda to the alpha. Right? That's the definition of C and CB. And you are equating them. So this allows us to find a formula. First of all, lambda BF is lambda IA, that we already know. But this also allows us to calculate CB and CA relation. So CB, this is of course the same as CB over lambda I to the A, because lambda B is lambda IA, that we already have here. So lambda I. Yeah. So lambda I A to the power beta. I mean, I should have put a B here. To the power beta. So this is lambda I A to the power alpha to the power beta. Is this okay? Okay, if it's not clear, let me repeat again. So this equal to any, right? Lambdas, as it passes through, lambdas of course are equal, right? Because it's the same lambda after all, that is describing from matter to radiation. This tells us that this is the definition of when you make transition from B to A, right? When the energy densities in matter and radiation are equal, or energy densities in B and A are equal. So this relation will translate now into relation of lambda, because rho is C over lambda to the alpha or lambda to the beta, because beta is a corresponding exponent for B. So this gives you CB over lambda BF to the power beta, because this is rho final time. This is rho at initial time for A, that's CA over lambda I and A to the alpha. Then you use the fact that lambda FB is the same as lambda IA to rewrite this as CB over lambda IA to the beta. So CB then is given by CA times lambda IA to the power beta minus alpha. Is this clear? Okay, if it's not clear, please let me and we can discuss it again. Okay. So let's now go ahead and calculate. Okay, we will not calculate anything. We will use exactly this formula to calculate RH of TF B minus RH of TF TI. Beginning of B to end of B. Okay, why are you calculating this? Because you want to, eventually our goal is to argue that this will be negligible compared to what we will get in A. Okay. What we get in A is given by this formula. What we get in B will be given by similar formula. With all these alpha, beta, etc. Alpha will be replaced by beta, these will be replaced by the corresponding lambdas and so on.
The C will be replaced.
C will be replaced by CB and so on. So this, we use the same formula. So 1 over A naught, 2 over beta minus 2, 8 pi G CB over 3 to the minus half, and then here you get lambda F P to the power beta by 2 minus 1 minus lambda I B to the power beta by 2 minus 1. Again, this part is small, can be ignored. if beta is greater than 2. Okay, for example, if B is radiation, then beta is 4, right? So obviously that's greater than 2. And lambda in fact is 0, right? Because you start from Big Bang. The standard Big Bang scenario, you start from lambda equal to 0. So initial data in the Big Bang in the radiation dominated data is lambda equal to 0. So you only really need to look at this term. So now the idea is that we will express everything in terms of A, right? So CB and CA relation we already know. So we get this 1 over A naught 2 over beta minus 2 8 pi G, and then we put the extra factor lambda A to the power. This is beta minus alpha, but there is a minus half. So minus half times beta minus alpha. And for this, we put lambda A to the power beta by 2 minus 1. Okay, let me do one thing. So I will put lambda A to the beta by 2 minus 1, and then I will write as 1 minus lambda B over lambda FB to the power beta by 2 minus 1. Okay, so this is small. I have kept it 10 here, but this is argued to be small. Okay? Because I have just taken this factor out and taken this ratio here. So after putting all this, okay, now you see that this is 1 over A0 2 over beta minus 2 8 pi G CA over 3 to the power minus half, and here we have lambda AI. Okay, let's calculate the total power. Okay, you see here it's beta by 2 minus 1 minus beta by 2, so that cancels this beta by 2 plus alpha by 2. Okay. So this gets converted to alpha by 2 minus 1. And then you have a factor which is almost equal to 1, but let me write this lambda B over lambda FB, which is the same as lambda A to the power beta by 2 minus 1. Is this okay?
That is B prime sub lambda equal to
No, B is that's B. Okay. Now the idea is that we will compare this with this. Okay. This is the amount by which RH will change in the matter dominated area or in the A dominated area. Right? This is the amount by which RH has grown in the B dominated area. Now we see that 1 over A naught of course is common. Here is 2 over beta minus 2, here is 2 over alpha minus 2, but these are both numbers of order 1. Right? Beta is 3 or 4. This factor is common. Right? In A dominated area, this C will be replaced by CA. Okay? This factor is exactly the same as that. Here you have lambda A to the alpha by 2 minus 1. That's this term, second term. Right? But you have already argued that the first term dominates the second term. Right? If you wait a little bit in the A dominated area. So all that this does, right? The whole evolution in B, all the way from the beginning till the crossing, is simply add a little bit to the second term. Okay? But it's still highly subdominant compared to this term.
Can you
Yes. So what I am saying is this term over here, right? is of the same order as what you get by if you pick the second term. Because all the other factors are more or less common, right? Except for factors of order 1. But this is small compared to this that we have already argued. Okay? So which means that this factor that we get from the whole evolution in the B is small compared to what you will gain in the matter era. Right, or in the A era. Okay, if you wait for a little while in the A era so that the lambda expands by a certain factor, okay, then the dominant contribution comes only from this term. Right, you can ignore whatever happened before. Is this point clear? Okay. So the point is RH acts, right? RH acts. So if you want to calculate RH at any given era, in principle you should find RH for all the previous eras and add them up. But what is this argument is showing, at least in the cases that we know of, matter and radiation, that contributions from the previous era can be ignored completely because they are actually small compared to what you will get from the final era. Okay, as long as you wait for sufficiently long in the final era. Is that point clear? Okay. So in practical terms, okay, we have radiation dominated era since the Big Bang, and then it gets converted to matter dominated era. What this is saying is that if you want to calculate the horizon, say well into the matter dominated era, you can ignore the contribution from the radiation dominated era. Okay, because that will only contribute this much. Okay, which is of the same order as the second term in this expression. But the dominant contribution, you know, comes from the first term, right? The second term is negligible compared to the first term, which means this is also negligible compared to the first term. Okay. And this happens simply because lambda is growing. Okay, and lambda here comes to the positive power. Okay. So if lambda is growing, right, then the later you wait, the more you gain. Okay. That's the reason why the horizon in the early era is highly subdominant compared to the horizon in the later era.
Sir,
Yes.
this is valid. You have shown in only for the case when it goes like C by lambda to the power alpha.
Yes.
So, but physically, if we try to see, then lambda if dominates over lambda I, then it's looking like we can actually always do such thing. Is it like that?
Oh, as long as alpha is greater than 2. We'll come back to what happens when alpha less than 2. Okay, because we have argued that for this to happen, the second term has to be suppressed compared to the first term, right?
Yeah, what I'm saying is if second term can always be suppressed with the first term,
Yeah.
then we can always do such.
Then you can always do such things, exactly.
It's not necessary that it should be rho C by rho should go as C by lambda. To the
No, you can change it. I mean, you can take superpositions or something else. But the point is, there is some restriction on what kind of behavior rho should have. Okay. I have taken rho equal to C over lambda to the alpha because that's the typical behavior one gets, right? In one component, if one component dominates, okay, it comes from there. Okay. Or another way of saying that if you take the equation of state to P equal to W times rho or some constant W, then you get this kind of behavior, okay, between rho and lambda. Okay, so now let's consider the physical situation of interest. So we evolved from the Big Bang. This is T equal to 0. This is P of matter radiation equality. This you saw happens at lambda of order 10 to the minus 4. Our interest was in calculating the horizon size at the time of last scattering. So this is TLS. Okay, last scattering surface. This happens. It's also known as recombination, okay, because that's when the electrons and protons are combining into hydrogen atom. So this happens at lambda of order 10 to the minus 3. Okay, so later than the matter radiation equality. Now, while it's true that in this region, okay, it's not that radiation is negligible compared to matter, they are more or less of the same order. By the time you have gone here, the radiation has fallen to about 1/10 of matter. So, if you are interested in the order of magnitude estimate, you can ignore the radiation contribution. You can pretend as if from here to here there is only matter domination. Okay, again there will be an error, but the error will be of order factor of 1. So, you can use then this formula. Okay. So, if you want to calculate B, the RH at T last scattering, you can use the matter domination formula. This formula, okay, for matter. So that will be given by 1 over A naught. So then alpha is 3 for matter domination. So 2. So this is alpha equal to 3. Formula we are using 8 pi g Cm over 3 to the power minus half, and then this is lambda of last scattering to the power, alpha is 3, so 3 by 2 minus 1, that's about half. If you want, you can subtract lambda of matter radiation equality to the half, but this is still a factor of 3 more than this one, right? Because lambda LS is factor of 10 more than lambda of equality. Okay. When you take the square root, it's still a factor of 3 more than this one. Okay. So you can will ignore it. Okay. So I can put an order of magnitude here. Is this clear? Okay, is it clear what we are doing here? This was the formula for RH, right? We are using this formula. We are using the fact that this phenomenon that we are looking at, okay, the last scatterings are scattering time period, that happens in the within the matter dominated era. Okay. So you can use the formula for matter dominated era with appropriate factor of alpha. Okay. And then you are using the fact that because we have already stated about 10, the lambda is expanded by a factor of 10. This is 10 to the half opposed to this one, which is half, 1. Right? Lambda f over lambda ratio is 10. Okay. So you are ignoring this 1 compared to 10 to the half. Okay, because basically that means that instead of using 3 we would have gotten 2. Okay, we are just using 3.
Sir, in this last one also you are doing the same thing. Initially you are removing, like practically ignoring the first term in writing RHTLS.
Yes. Yeah. So you are ignoring first of all the contribution from the radiation dominated era. Okay. Because that R good will be small, that will be of this order. Okay. And then you are also ignoring this term.
But this integral correctly is between TLS and TE equilibrium, right? This
Yes, so the full integral should have been between T0 to TLS. This part we have argued is negligible because it is of the same order as this. This integral gives you this, assuming that it is fully matter dominated, and then we are using the fact that this is small compared to this. Okay? But small compared to this only means that it is a factor of 3 smaller. But that is good enough for us because we are calculating order of magnitude. Is this okay? So this gives you roughly an estimate of how big the horizon was at the time of last scattering in the co-moving coordinates. Okay, you can multiply this by A of t at that time to get the result in the physical, how much was the physical distance, physical horizon size. Okay, that would have also gotten rid of this A0 which is sitting below. So now we are going to ask a slightly different question, okay, but which will also be related to this horizon calculation. The question that we will be asking now is the following. Let's now shift our coordinate system and assume that we are at r equal to 0. We are sitting at r equal to 0 and we are looking in two opposite directions of the sky, in this direction as well as in this direction, and we are collecting microwave photons which are coming from two opposite directions. So there is, as I said, there is a hypothetical surface of large scattering from where these photons are traveling to us. Okay, since the time of last scattering, most of the photons that we are receiving haven't scattered. Okay, so you can think of these photons that we are receiving having originated at the time of last scattering. So we want to calculate this distance, but we will calculate this distance in the co-moving coordinates. Okay, so that we can directly compare with that RH that we have there. Okay, because that's also given in co-moving coordinates. So what will be the distance between this point and that point in co-moving coordinates? Okay, that will tell us that how far apart the 2 points, these 2 points, okay, where the micro radiation is coming from, were at the time of last scattering. Okay, you can directly compare with this RH that appears there, because both will have to be multiplied by appropriate factor of A at the time of last scattering. Okay, so this is given by 2D. Okay, you have to calculate D.
So DD isn't it that RH and that of LS?
No, it's not RH at LS. Okay, we'll calculate D. Okay, so how do you calculate D? See, its calculation is very similar. So this is T at last scattering, right? This is T naught. Okay. Again, light is traveling along null geodesic from here to here. Okay, so you have to use the same null geodesic formula. So we have to use the fact that integral of 0 or TLS to T naught dt prime over A of T prime is integral 0 to R dr prime. If this is at location R. But this distance is what we are calling D. Right, in co-moving coordinates. Okay, if K was 0, then R and D would have been exactly the same. Okay, maybe D I have used because DH may get confused, so let's call it delta. Okay, that's why it distinguishes from anything else that we have introduced so far. Is this okay? But this side can be written as integral from 0 to T naught dt prime over AT prime minus integral from 0 to TLS dt prime over AT. Right? So this side is nothing but RH of T naught minus RH of LS, TLS. So you conclude that delta is RH of T naught minus RH TLS. This was the definition of RH of T. Okay. Now RH of TLS, of course, we have already calculated. It's here. It's here. How much is RH of T naught? You have to do this integral. Okay. So again, we will make an approximation. Okay, we know that during from TLS to today, much of the time the universe has spent in the matter dominated era. Right? Recently it got converted from matter to cosmological constant domination. Okay. So again, at the cost of making an error of order 1, okay, we can pretend as if it was matter dominated all the way from TLS to today. Okay. We'll make an error of order 1, but again we are not worried about errors of order 1. Okay. So we use the matter domination formula for this. Okay, which is already here. Okay. So this will be given by 1 over A0 times 2 over alpha minus 2 8 pi g c over 3 to the minus half, and then lambda naught today is 1 by definition, right? So lambda naught is 1. This is lambda naught minus lambda ls to the power alpha is 3, so that's half. This is 10 to the minus 3, right? So 10 to the minus 3 by 2, small compact to 1. Okay, so it's basically of order 1.
minus 3.
Right? 10 to the minus 3 by 2 is small, it's at least smaller than 1/10. So this is of order 1.
I don't get. We are not in the matter dominated era.
Yes, that's right.
So using this.
The point is that again the change, we are not in matter dominated era, but nevertheless the matter is still there, right? It's 0.27%, 27, right? So between matter dominated era, so you can say, okay, we will not calculate, we don't want to calculate RH at T0, let's calculate RH a little earlier, okay, when the universe was still cosmological constant, matter dominated, right? So lambda is 1 today, right? If you take lambda to the half, then matter would have been 8 times more significant, right? Because it goes as 1 over lambda cube versus 1. Okay? So let's say that we don't want to calculate RH today, right? RH today is certainly more than RH some time ago, right? So you can put a lower bound on RH on delta by calculating RH at T0 by 2, or not at T0 by 2, RH at a time when lambda was half of what it is today. Okay, then it would have been matter dominated. Is that clear? Okay, so lambda naught instead of 1 you would put half.
So in principle, if you want to do experiment today,
Yes.
then you should include those.
Yes, you should include. That will change RH, but at least it will not be less than what it was when lambda was half, right? Because RH is increasing. But this integral, if we write this integral from Ts to T0, I can always write TLS to T0 by 2 and then plus T0 by 2 to something, right? So I am saying just TLS to T0 by 2, right? That integral will have the effect that instead of having this 1 over here, okay, you will have some other factor to the power half, right?
So
Maybe half to the power half.
And the other factor, the other term that
This is still 10 to the minus 3 to the power half.
And
Other terms will add to it.
yeah, that's that it should be, it is half, and there is also TLS to T0 by 2, what you are saying.
Yes, so that will be added to this. That means this is at least a lower bound on what delta is. Delta is at least this much. It's more than this, right? We don't care. We have to find a lower bound on delta. Right? Because you will see that we will try to show that delta is too big compared to DH. Right? That's the contradiction that we will be trying to discover. Okay? So you want to find a lower bound on delta. Okay? So if you don't want to trust this calculation, you just stop our analysis at lambda equal to half. Okay, where the universe was certainly matter dominated. So 2 over alpha minus 2, alpha is 3, so this is just 1. This is just 2. Okay, so now we are in business, because you see we want to calculate now RH of TLS over 2 delta, because we want to see how this distance compares to the horizon size. Why? Because we know that the radiation is uniform over this distance. Whereas horizon gives a limit of how far the points could have been communicated in the past. Right? So if you are trying to invoke thermal equilibration, okay, to explain why the universe is so uniform, okay, it cannot explain anything beyond the horizon size. Uniformity beyond the horizon size cannot be explained by thermal equilibrium process, right? Because there is no way the 2 points further than the horizon distance RH could have ever communicated in the past. So you have to calculate this ratio. If this ratio is 1 or more, then you are okay. Okay, because then the horizon size is larger than the distance over which you are sure that the universe was uniform. So let's calculate this ratio. Okay, now that's very easy. All of these factors are really the same. This is Cm. Okay. So this ratio is basically lambda ls to the power half over lambda naught to the power half. Okay, let me write lambda naught, because if you are not in, if you don't want to put lambda naught equal to 1, you will put lambda naught to the half. Okay, we can stop at wherever you want. Okay, lambda naught equal to half, you can stop. Okay, where there is a confusion about whether matter was dominant or not.
So lambda naught minus lambda ls also calculate.
Pardon?
Lambda naught.
But this is always small compared to this. This is 10 to the minus 3, this is half, right? So it's still much smaller than this. Okay, you can ignore this.
So why this RH minus delta that
Why? Because this is the horizon size
at the time of last
at the time of last scattering. This is the distance at the time of last scattering, okay, that you know over which universe was uniform. See, because we are receiving signal here, but from these surfaces, right?
Oh.
And because you are using co-moving coordinates, okay, the distance in the co-moving coordinates you can compare directly. Okay, otherwise if you have physical distance today, of course it's very different from physical distance earlier. Okay, so we have calculated the co-moving distance, you have to multiply by A of t at last scattering to get the physical distance between these 2 points where the radiation is coming. But you have to do the same multiplication for this also. So this is the horizon in the co-moving coordinate. The physical horizon was this multiplied by A of t ls, right? So A of t ls will cancel. Okay, so as far as the ratio is concerned, it doesn't matter whether you use co-moving coordinates or physical distance. You have to make sure that you are using the same metric to calculate the two.
Okay.
That's why this ratio is important. Okay, this is the distance, maximum distance 2 points could have communicated. Okay, this is the distance over which you are sure that the universe was uniform. Okay, from today's observation, apart from the background, because the temperatures in this direction of the sky and that direction of the sky are the same.
So it means you are saying that we should get minimum possible delta so that if we can be sure.
Yes, exactly.
That's why I'm saying if we include minus lambda ls, it will be more accurate.
Yeah, you can include it. But what I'm saying that how much change you need to make, right? I mean, this ratio is not going to change very much by that. So you see that this ratio is in fact very, very small, right? Why? Because this is 10 to the minus 3. Right? This is order 1. Okay? So this is much, much smaller than 1.
Sir,
Yes.
the 2 points here we are checking the light is coming and
Yes.
so from here only you can actually see RH should be very, very less than 2 delta. Can't you? Because RH TLS is the one, the light assume at that point wants
Yes.
to communicate to that another point.
Exactly.
That is lying just opposite to the point. So if you want such a thing, then RHT light has till now reached only to a point till
That
RH
is true,
equals to
yes.
0.
Yeah. So you can, a factor of 2 you can easily explain. Right? Till now we have only, light has only reached up to this point.
Yeah.
It still has to go same distance
Yeah.
to go to the other point, right?
Yeah.
So that explains, that gives a factor of 2. But here this is much more than a factor of 2, right? This, because of the scale factor, you are getting also a bigger factor. See, that factor is this half that you are talking about, right? But on top of that, this factor you have to do some work to calculate, right? That at the time of last scattering, okay, line should have traveled much smaller than this distance. Okay, how much smaller? That's this factor, lambda ls to the half over lambda naught to the half.
But what I am saying is the 2 points which are 180 degree apart, and I am looking at them.
Yes,
They will be actually always be outside the horizon.
I agree. They are outside the horizon even today.
Yeah.
Okay, but that only gives a factor of 2 because today's horizon is this much,
Yeah.
right? So there you could only conclude that they are out of the horizon, but only by a factor of 2.
Yeah.
Okay. If you want to actually calculate how big is the error by which you are outside the horizon, right? You have to actually calculate the horizon size then.
There.
Okay, that gives this extra factor of lambda ls to the half.
So we should compare it at that time. Why we comparing this uniformity of the now?
Because the signal that you are receiving today originated at that time,
Yeah.
right? So if we are seeing the same temperature on both sides, that means at that time the temperature here and temperature here are the same. No? Because the photons haven't changed anything after they got emitted, right? Okay, because at the time of last scattering, that's the last time they scattered with anything else, right? After that they have been traveling freely. They had no chance to do any thermal equilibration or anything after the time of last scattering, right? And that is the reason why what we are seeing today gives us information about what was the state of the universe then, right? If the photons had scattered a lot in the intermediate immediate time, right, then of course you can make no such conclusion, right? The photon temperature could have uniform, okay, because of the subsequent scattering. But because we know from calculation of photon scattering cross section that the probability that a photon emitted at that time would have scattered before reaching us is very, very small. Okay, so most of the microwave photons that we are seeing today have not scattered since the time of last scattering. Okay, and that is the reason why what we see today tells us how uniform the universe was at that time.
We can see also in this way that when the universe was at that time, the distance by which the light travels, that should be the equilibrium distance.
Yeah, naively we would think that that's the equilibrium distance, but from our observation today, right?
That is much more.
That is much more. That's what I said. We are seeing that the universe was uniform on a much larger scale than what you could possibly expect from thermal equilibration.
Oh,
Right?
Alright.
Thermal equilibration, you can expect that the universe will be uniform over a distance scale of this, maximum distance scale of this. Right? To thermally equilibrate, you have to communicate by several times. Right? Just one signal from one point to another point will not achieve thermal equilibrium. Okay? But you have to at least send one signal to thermal equilibrium. But this is that maximum distance. Whereas from our observation today, we know that the universe is uniform over a distance scale of this kind. Okay? And that is the problem of causality, that how did the universe become so uniform? Is this point clear? Okay, that this uniformity of the universe wouldn't be explained just by assuming that at some point the universe was in thermal equilibrium and hence that made everything uniform.
So it means that at that time when those photons released, at that time these 2 points,
Yes.
though they were in the inside that RH.
No, they are not inside RH. We calculated, see the distance that we calculated is not today's physical distance but the co-moving coordinate distance, right? Those are fixed points in space time as it's expanding.
Oh, okay.
So that's what you're comparing, right? So if we want to calculate what is the physical distance at that time, we have to multiply by A at T last scattering.
Yeah, but it is the inside those 80, that metric. And that is fixed over all time.
Yeah, the point A of T last scattering is the same, right?
Mm-hmm.
It's the same factor that you have to multiply both this distance that you calculated and RH.
Mm-hmm.
Right? So in the ratio it will not matter.
Yeah.
Okay. But if you want to calculate the physical horizon at that time, it was A of TLS times RH.
Mm-hmm.
Okay. The physical distance between these 2 points at that time was A of TLS times what you have calculated, 2 delta.
Okay.
Okay, it's rather A of TLS because it multiplies both the numerator and denominator. We can forget about A of TLS, right? Because we are just only calculating ratios.
Mm-hmm.
Is this point clear?
Yes.
Now, to see how severe the problem is, we can ask the following question. Okay, so take this diagram over here, and let's imagine that we don't look at diametrically opposite points, but we look at 2 points at an angle delta theta apart. And so you can ask, what value of delta theta corresponds to horizon size?
Mm.
Because uniformity over that value of delta theta could in principle be explained using equilibration. Beyond that, we cannot explain
So horizon size at the last scattering.
at the last scattering time.
Mm-hmm. That RHLS.
RH of a TLS.
And sir, always that delta theta will be less than 5 because
Yes, obviously, because we calculated it, right? It was much more than this.
because
So,
physically also you can see that because
I agree, because this is only the maximum distance it could have been, right? Without doing any calculation, you could have said that the maximum distance I could have traveled is delta, not 2 delta.
so in any case sir, you cannot make it uniform.
Yes, but you want to know how far you are missing, right? Because if you want to repair this problem, okay, you have to know how much you have to repair, right? Because of course, if you are only interested in showing that there is a problem and you don't want to do anything about it, then you don't care, right? But eventually you want to see how to get around this problem, okay? And for this, it's good to know how far we are missing it by, right? Okay, it also has various other features that I will try to explain. So this calculation is not very hard. So the equation that we have to solve is basically delta times, well, let's call it delta theta, so that there is no confusion. Delta times delta theta is RH at TLS. This is delta theta measured in radian. Okay? Because this distance, radius times angle, okay, that distance you want to be the horizon size at that time. So delta theta is RH at TLS by delta, which is lambda LS to the power half. Okay, I will not take lambda enough equal to 1. Okay. So this 2 is not there, so it's basically RH of TLS by delta that we have calculated. So this is 10 to the minus 3 by 2. Because lambda LS is 10 to the minus 3. So if you want it in degrees, it's 10 to the minus 3 by 2 times 180 degree by pi. Okay, you can calculate it, so you will find that this is about 2 degrees. Is this clear? So this tells us that if the uniformity was within 2 degrees, we could possibly try to explain it, okay, because things should have communicated. But uniformity beyond 2 degrees cannot be explained. Is this clear? But this also has a different way of interpreting it. We can say that, imagine that we found some mechanism which repairs this. Okay? So that whatever that mechanism is, that mechanism will be seen intact in the sky if we look at fluctuations or correlations at angular scale larger than 2 degrees.
Hmm.
Because at angular scale larger than 2 degrees, right, there could have been any correlation, okay, by standard known physics.
Hmm.
Right? Because there would have been no communication
Hmm.
by standard known physics at an angle of less than 2 degrees.
Okay.
So any correlation, any information about the correlation that we can see at an angular scale larger than 2 degrees, okay, is directly a measure of what actually made things uniform. Okay, because any mechanism that made things uniform, right, presumably would give how things are correlated. Okay, it's not exactly uniform, so there is a fluctuation. Right, so you could calculate in principle the 2-point correlation function, okay, between temperature here and temperature there. So those are will be completely unaffected by the usual physical theories. Okay, what we know about the usual physics, if we measure the correlations outside the 2 degree angle, because there could have been no communication by standard physical laws, okay, at that scale.
These fluctuations that we see outside 2 degrees,
Yes.
that can be thermal fluctuation also.
No, it cannot be, because the point is any fluctuation that you see outside 2 degrees, any fluctuation that we see outside 2 degrees cannot be affected by any thermal fluctuation, right?
Yes.
Because any thermal fluctuation, right, which tries to uniformize things or maybe give some correlation, that can only work up to 2 degrees. Okay? Because beyond 2 degrees there is no communication.
So beyond 2 degrees, that correlation, that won't be a thermal correlation.
That it cannot be explained as thermal correlation.
There is a concern that suppose before this uniformization happened, suppose there was some thermal fluctuation that was created between 2 points.
Yes.
After uniformizing, they went to be
Fine. So that could have been seen, right? But those had to happen before this uniformization. Right? So what I am saying is that if we say, so the way we will try to address this is that we will say that at some point in the time scale, right? So this is say T equilibrium, this is radiation, this is matter. Okay? That at some point some new physics takes place.
Yeah, because
So we have to discuss what that new physics is. Okay? From here onwards it's usual radiation dominated, then from here onwards it's matter dominated. Okay? So what I am saying is that anything that happens, okay, that any correlation that you see outside 2 degree angle must come from here.
Yeah.
How they come, of course that depends on a new physics. Okay? But physics, anything that happens here cannot affect those correlations. Right? So in this sense, that any correlation that you measure outside this 2 degree angle is directly a measure of what was happening here.
So new physics is before T equal to 0, you're saying?
Well, we don't not declare T equal to 0. T equal to 0 was where lambda become infinite. Lambda becomes 0, right? Now you are saying that even before that happens, some new physics takes over. Yeah, so this is some T equal to epsilon.
Where radiation starts to dominate.
Yeah, so after this, the usual radiation dominated era comes into play. Because that we know, some part of the universe had been radiation dominated, right? Because if we see the universe today and extrapolate back, we can see that it would have been radiation dominated before TEQ, and no known new physics takes over before that, right? We understand physics at low energies very well. So if there is a new physics which takes over, it has to be at sufficiently high, sufficiently early in time, but the temperature of the universe is so high that it's beyond what we can explore today.
But you integrate for RS, you integrate from 0, not from epsilon, right? So like,
Yes, exactly. So from epsilon to TEQ, we have seen that it cannot help us, right? We did the integral of radiation dominated era from epsilon to TEQ.
Not from
sorry,
0.
I'm interrupting. The premise is that the maximum distance that is available to a light signal is RH actually, from the start T equal to 0 to whatever the point.
Exactly.
No distance in this universe for a light signal is greater than RH.
Yes.
So anything that falls outside RH is beyond the causal connection that can be.
Exactly. That's right.
That is the similarity that you have contradiction that is happening. So what you are saying with this new physics, I cannot understand.
Yeah. So what would have happened in this new physics? Okay, is that RH is added, right? Okay. So RH would have become very large at the end by the end of the new physics. Okay, from the beginning of the universe till the end of the new physics, okay, RH will have to grow to a sufficiently large size that can explain this discrepancy.
So these farther points are in equilibrium actually, which are.
Yes, because if RH had grown, right, then they could have been in equilibrium before this happened, right? That could have explained why they are uniform. See, the point is we don't, in order for this to be uniform, they don't have to be in equilibrium here, right? If they are in equilibrium some very early in the past, okay, which had made them uniform, then they remain uniform because it's the same laws which evolved them, right? So they don't have to be always in equilibrium all the time throughout this evolution, right? If you set them to equilibrium, okay, at a very early time, okay, and then if the laws of physics are the same in different parts of the universe, which of course you expect to be the same, then they would keep evolving in the same way and they'll remain uniform. Okay. So the idea is that RH had to grow enormously here, okay, so that even though if we count from here, okay, then the 2 points outside the apparatus horizon couldn't have communicated. They could have communicated somewhere far back in time. Okay, and they could have uniformized themselves somewhere there. So that will be the criteria that you have to satisfy. Okay, that somehow RH should have grown at early time.
Then how is it possible? Like your signal only travels at C, right?
Yes.
So
Well, how is that possible? You can now go back to this formula and you can see. Okay, we saw that as long as alpha is larger than 2, this is bounded by this, okay, which makes it smaller than how much it would get contribution in the next era. But if alpha is less than 2, okay, then this coefficient is negative. Okay, there is a minus sign, but that minus sign is cancelled by this minus sign. Okay. And now it could happen, okay, that this, because lambda I is small, this factor could have become enormous. Okay, so we need some kind of matter or some kind of source for which alpha is less than 2. Okay, you cannot solve this problem if you assume that whatever happened in the past always had alpha larger than 2. Okay, radiation replaced by matter wouldn't have solved this problem. But if you can replace radiation or matter by some other equation of state for which alpha is less than 2, then in principle this problem could be solved, because then this could become very large. Okay, you could have got a large contribution in the interval, okay, which precedes what we know.
But why that interval will be small?
Why that interval will be small?
That you are putting like t equals to epsilon kind of.
No, t equal to epsilon is, I am not claiming that t equal to 0 is the beginning now. See, but t equal to 0 you have defined by saying that that's where the lambda would have gone to 0, right? So now, okay, the origin of time doesn't matter. You can call t equal to 100 plus epsilon, right? We had defined t in such a way that if we had assumed that the Big Bang, the radiation dormitory era continues all the way in the past, then t equal to 0 would have been a point where lambda becomes 0. Right? So we can keep the same definition of t, right? That if we ignore new physics and just continue past, then at t equal to 0 lambda would have become 0. But once new physics takes over, then there is no reason, I mean, you don't know that lambda actually becomes 0 at t equal to 0, right? So this interval is dynamic, it has to be determined by seeing when lambda is becoming 0.
So then you don't have photons before epsilon?
Well, you could have photons, but they will be subdominant. The dominant contribution should be some kind of matter for which alpha is less than 2.
So here again you will define your time t equals to 0 as the when lambda goes to 0.
Yes, see the time t equal to 0 doesn't really play a role. That's why whenever I solve the equations, I put a constant t plus k to the alpha, right? So none of the results that you have gotten, right, depends on where you have chosen the origin of time to be. Right? So when I am saying t equal to epsilon, right, It's just that if we had used the standard Big Bang theory, right, where T would have diverged, or lambda would have become 0, right, you choose, in the conventional Big Bang theory, that's where you choose your origin of time. Right? So, in that unit, we know that till T becomes very small, the temperature wouldn't have risen, right? T goes as 1 of, the temperature goes as 1 over lambda, right? And lambda goes as some power of T. Okay? So, for the temperature to rise sufficiently high, where you don't know what physics is, right? Because you haven't performed experiments, T has to be sufficiently small. In that way of choosing the origin of time. Okay? So, a better way to say that T you can forget, right? Instead of leveling by T, you can level by lambda. Okay? So, here lambda should have been very small. Okay? How small? It has to be at least smaller than the known physics, right? The T goes as 1 over lambda. Okay? So, we understand the dynamics of the universe very well till 100 GeV. Okay? So, nothing less than 100 GeV could have possibly worked. Okay? We cannot change the laws of physics at less than 100 GeV, right? We don't know of any kind of matter which satisfies alpha less than 2 at less than 100 GeV. Okay? But it could have happened that when you go far high in energy, okay, which requires the lambda should be very small, okay, that the laws of physics change and you could get kind of matter for which alpha is less than 2. Okay? In fact, you already know of a kind of matter where alpha is less than 2. That's cosmological constant.
Yeah.
Right? And that's what you are going to use. Okay? That's one of the that's the most popular model of inflation. Okay? That you just use a cosmological constant, okay? And that solves the problem. Okay? That basically gives a very large contribution to RH, okay, which could resolve this discrepancy.
So, but if we take a cosmological constant, then you will keep on increasing.
No, so a cosmological constant has to be not really a constant within the form of a potential for a scalar field. Okay? So there has to be a dynamics of the scalar field in which the potential can actually change from a large value to 0. Right? See, if it's a potential of a scalar field, right? The scalar field as it moves, the potential can change, right? So the idea will be that in the early universe, the scalar field was having a value where the potential was large. As the universe evolved, the scalar field also started moving, and this is the point where the scalar field rolled down, it lost the potential and everything became radiation.
So the cosmological constant that we see today,
That's different.
lambda, that will also be like a scalar field.
That could be the potential of a scalar field.
But
Right?
there's no certainty that it will.
No, because it's not okay. The point is, it's not the most likely it's not the potential of a scalar field which is moving. Okay, because then there will be a massless scalar field that you would have discovered in experiments. Okay, but it could be simply that you are at the minimum of your scalar field potential, right? And there is some other global minimum when the scalar field vanishes, or when the scalar field is such that the potential vanishes. Okay, that is certainly possible. Right? And in fact, most of the models that try to accommodate cosmological constant are of this kind. Okay, there is some kind of local minimum of a potential. Okay, where the energy density is non-zero, the cosmological constant potential is non-zero. The global minimum will have potential equal to 0. But the kind of potential that we have to use are not like a local minimum of potential. Because if it's a local minimum, the scalar field will get stuck there.
Yes.
Right? It cannot move out, at least not classically.
Yes.
Okay? So it has to be some kind of flat potential where the scalar field is rolling around the potential. Right? The potential remains almost constant, and that's why it acts as a cosmological constant. But at the end, okay, it somehow rolls down, right? Because the potential is such that it's flat for a while and then it drops. Okay, and that is why it will end this particular phase of the expansion. Constant, but which all have to use an equation of state for which alpha has to be less than 2. Like this is the model independent statement. Okay. Unless you have some kind of matter for which alpha is less than 2, this problem is not solvable. Okay, because you cannot get large contribution to the RH. Okay. To get in the otherwise basically the earlier you go, the less your contribution to RH. Okay. The only way you can get large contribution to RH is if you use some kind of matter for which alpha is less than 2. Okay, so I think we'll continue on.
So in this case, delta won't also increase. Delta.
Yeah.
Because delta also contains that term which we neglected. There's 1 minus lambda ls.
Yes.
That lambda ls.
Yes, but the point is that you could have that term, okay? But delta typically is very big. Okay. But yes, I mean, otherwise delta could contain that term. It will not make any difference.